My name is Ensar Basri Kahveci. Today I'm going to talk about some general topics in distributed systems theory and their practical implications we can face when we build distributed systems products. Let me first introduce myself. I live in Ankara, the capital of Turkey. I've been working for Hazelcast for 2.5 years. Hazelcast is a company that builds an in-memory data grid product with the same name. Basically, it's a distributed caching solution that works in memory. And my job title is distributed systems engineer. So I work on core modules of the product like cluster management, data replication, fault tolerance, and stuff like that. So within our company, we have been studying distributed systems topics to understand how our solutions fit to the theory, how we can fix our internal problems and make our product more reliable. And we experienced that this field is a little bit difficult to study, but eventually our effort turned out to be fruitful, and we have made a lot of improvements in the system. So this talk is mostly based on the stuff we have studied for our own work, but I can say for sure that I am not an expert in this field. I am just a mere mortal that tries to understand this field. You know, I'm eager to study it and work on it, build products that actually work fine on top of this distributed systems field. So I will first talk about Hazelcast and mention some of its distributed systems related aspects, and then we will go into some theoretical topics, and as we go through them, we will mention practical stuff, and we will also mention Hazelcast as it becomes relevant to the topic we are discussing. So Hazelcast is the leading open source in-memory data grid written in Java language. It is free to use, and it is known for its simplicity. It gives you distributed implementations of Java Collections API. So if you are familiar with Java maps, sets, queues, it means you are already familiar with the API of the Hazelcast. It just works in a transparent way behind the same interfaces. And we also implement the JK specification of Java language, and we have some other distributed data structures. But it is not only a data storage solution. You can also perform distributed computations on the data you store in your Hazelcast clusters, or you can use Hazelcast as a lightweight messaging layer in your infrastructure. It is just a single jar file. So you can embed it right into your application, and it can scale at the application level with your own application instances. Or you can use it with the client-server deployment model. So although the server is written in Java, we have client implementations in many other languages. And Hazelcast integrates with many tools, frameworks, libraries, cloud platforms, discovery services quite easily. I can mention some aspects of Hazelcast about being a distributed system. So first, it can give you both scale up and scale out capabilities. So it is okay for both vertical scaling and horizontal scaling. And it is a distributed implementation from day one. I think this is one of our strongest points. We have a very mature and battle-tested core module. And Hazelcast enables dynamic clustering and elasticity. So it means you can start your Hazelcast cluster with any size and change it at runtime based on your needs. It just automatically adapts itself by making minimum changes in the data distribution. And it distributes your data transparently by applying partitioning and replication. So partitioning means that it takes your data and divides the data into partitions. So each partition is a distinct portion of the overall data set. Then each partition is replicated to multiple nodes in the cluster. And this is completely transparent, and you can also configure it if you like. And if there are failures in the cluster, it just automatically recovers your data by using the backups in the cluster, and it remains available that way. So as a general definition, a distributed system is a collection of entities trying to solve a common problem. These entities can be called as processes, nodes, servers, machines. And most of the time I use the term node because that term is the one we mostly use while making development. So these entities are connected by a network, so they communicate via they communicate via passing messages to each other, and they do not access to each other's resources, and they have uncertain and partial knowledge about the system. So each entity has some partial knowledge, and it can be wrong and inaccurate or missing, and there is no single global entity in the system, in a way that it knows everything about the system momentarily. So we need distributed systems because the problem we are focusing on may not be no longer solvable using a single computer. And I believe the most prominent reasons are scalability and fault tolerance. So basically these are the goals. We want to build scalable and fault tolerant solutions. However, there are some difficulties or constraints that we will always encounter when we try to build such systems. For instance, in a distributed system, some nodes might fail while some other nodes just keep running fine. So there will be partial failures in the system. And it also takes time to transfer a piece of information from one node to another because of the speed of light. And last, the communication among our nodes can be problematic from time to time. So we need to deal with such problems. So this is where system models come into play. So to simplify design of distributed algorithms and distributed systems, what we do is we first select a set of abstractions and models and assume that the underlying environment holds all the properties defined in these abstractions. So basically they give us a precise definition of the system, and they help us to ignore all the irrelevant details. So a couple of examples are how our entities interact with each other in terms of synchrony, or what kind of failures they can perform, or how they make use of the notion of time in the system. So we will discuss this stuff, and we will also mention a fundamental problem in this field, which is the consensus problem. So we will evaluate some consensus algorithms with a high level, and then we will briefly talk about the cap principle. And as we go through these topics, we will also discuss how Hazelcast deals with them. Okay, let's start with the interaction models. So these models characterize the behavior of our entities, behavior of processes and links in terms of the passage of time. So please do not confuse them with synchronous or asynchronous programming. So these are different. So the synchronous model says that there are known upper bounds for communication delays and processing delays. So when a node sends a message to another one, it exactly knows how long it will take to get the response. So it can make some timing assumptions. For instance, it can use timeouts to detect failures, because if it waits enough and if it doesn't get the response, it means the other node is just crashed. But the bad news is we do not have such guarantees on the systems we built on top of commodity hardware, because networking layer can delay our messages arbitrarily, or we can put some requests into internal queues so that their processing can be delayed arbitrarily. But this is still a good model to design algorithms and develop ideas. And on the other hand, we have the asynchronous model. So this one says that there are no upper bounds for both communication delays and processing delays. Nodes run at arbitrary speeds, and it can take arbitrarily long time to transfer a message. So in this one, we cannot make any timing assumptions. We should perform the computation based on the incoming messages and the local information. And one important consequence is, in this model, we cannot distinguish between a failed process and a slow process. So, for instance, when I send a request but don't get the response, the other endpoint might be dead, or it might be just slow. There's no way I can distinguish it. And the real world is, somehow closer to this one than the synchronous model. And between these two, we have the partially synchronous model. So it says that generally our systems tend to behave in the synchronous mode. We can estimate some time bounds that will be respected most of the time. But since the system doesn't give us these guarantees in a hard way, it can happen that, because of some temporary problems, like network problem or some GC poses or unpredicted load on our processes, it can happen that the synchrony of the system is broken and these time bounds are just invalidated. So in those cases, the system is in the asynchronous mode. And actually, this is the one which is closest to the real world. And as you see, there's a hierarchy here. So if your system can tolerate, or if you build an algorithm that will work in the asynchronous model, it will also work in the other models as well. But in Hazelcast, we embrace the partially synchronous model. So we use an internal timeout mechanism as following. So a Hazelcast server can make an internal remote method call to another one, and it uses a timeout value. And most of the time, the timeout value just works fine, but it can happen that the timeout can occur before the response is received. So in that case, we just throw a operation timeout exception to the user, and it means that, okay, I send a request for you, but I couldn't get the response. So it means that your request might be processed or it might not be processed. I just don't know, and I'm not making any assumption, and I'm just making you aware of this situation. So the user becomes aware of this, temporary asynchrony in the system. And another fundamental abstraction is failures. So in a distributed system, our nodes can fail in many different ways. This is not a complete list, but I will talk about some of them. So the simplest failure is crash stop failure. So it means that a node crashes and it never comes back. It's completely gone. So if we want to tolerate this failure, we should not rely on recovery of that failed node. And after that, we have the omission faults. So it says that an omission fault occurs when a node cannot send a message which it is supposed to send due to its algorithm because of like internal buffer overflows or network congestion, and it causes losing messages. And then we have the crash recover. So as its name implies, a process crashes, and after some time, it recovers back with remembering its previous state. And this one can be quite tricky to handle because once the process recovers its state, it can notice that the things in the system might be changed and its information might be stale. And last, we have the arbitrary failures. For historical reasons, this one is also called Byzantine failure. So in this one, our nodes can fail in arbitrary ways. So they may not respond to our requests, or they can send wrong results to our requests, or they can lie about anything about the system. So this is just the chaotic mode. And again, there is a hierarchy here. If your system can tolerate this Byzantine failure, it means that it will also tolerate all other failures here. In Hazelcast, we assume that there will be no Byzantine failure in the system because most of the time you run the product in a controlled environment. And we handle failures up to the crash recover failure. And the trick we use to handle crash recovery is if a process or if a Hazelcast node performs this crash recovery scenario, it just changes its identity and joins back to the system as a new node. So the system considers this scenario as a crash stop scenario. And from the development perspective, it becomes easier to write the fault tolerance code of the system. So time is another fundamental abstraction in distributed systems. We often use time to order events in our distributed systems. And the ordering is particularly important because correctness of distributed algorithms rely on some order of the events that occur concurrently on the system. And we can use physical timestamps for this purpose. For instance, we have a configuration in Hazelcast which is called latest update map merge policy. So normally in a Hazelcast cluster, each data entry is updated by a single node. But under some failure scenarios like network partitions, a data entry can be updated on multiple nodes in the cluster. And once the failure scenario is recovered, these entries are merged, and the entry with a higher physical timestamp is chosen, and the other one is just discarded. And this approach is called latest update wins, and it is also used in many other tools in similar ways. But the problem here is, in our systems, we do not have perfectly synchronized clocks. Our clocks can drift back or forward in time, and when we use these physical timestamps, we may not be sure if they are giving us the correct order or the wrong order. And Google deals with this problem with their TrueTime API. So they deploy special hardware like atomic clocks and GPS clocks to their clusters, data centers, and they create an upper bound on the clock drift. And the idea is, when you get the current time, it gives you a time interval instead of a single timestamp value. And if you compare, and it guarantees that this time interval will contain the current time. So it means if you compare two time intervals and see that they are not intersecting, so you can use them to order your events. But if they have some intersection, it means that you may not know the exact order among them because of the clock drift problem, bounded clock drift problem. So it is a very good solution, very elegant solution, but we can make use of some other algorithmic approaches as well. So this is how we arrive at ecological clocks. It is also called Lamport clocks because it is implemented by Leslie Lamport, which is one of the masterminds in distributed systems field. So this is just an algorithmic approach, nothing related to hardware. So this approach relies on local counter values in our processes and the communication among processes to create some partial ordering among the events in our system. So it defines the happens before relationship, which is also called causality, because in distributed systems, we generally think that if two events occur in some order, first event causes the second one. So this is the general idea, and this is why we call it causality. And the algorithm guarantees that if your events have this happens before relationship, their logical timestamps will be correctly ordered. But I will not go into details, but this is the idea. And we use it in Hazelcast quite extensively along with primary copy replication. So for instance, in a Hazelcast cluster, there's a single master node who manages the cluster-related tasks like adding new members, removing new members, or changing the partition distribution in the system. So when it makes a change to this information, it propagates this information to other nodes by putting a logical timestamps, and each node applies these updates by comparing the timestamps given by the master node so that they will apply them in the correct order. But this idea has a shortcoming. If you know that any two events have this happens before relationship, this algorithm will ensure that their timestamps will be correctly ordered, so that's good. But the thing is, if you just compare logical timestamps of two events that come from two different servers, you may not be sure if they have this happens before relationship or not, because this information is not encoded in this algorithm. So for this purpose, we make an extension, which is vector clocks. So vector clocks are used to, infer if any two events in the system have this happens before relationship or not. For instance, in Dynamo-style databases, they are being used to detect, conflicting writes or conflicting data entries in the system. But in Hazelcast, we don't need it. Lamport clocks work fine for us because in the places where we use these Lamport clocks, we know that there is only a single node, performing these updates. So these were the basic abstractions, we will always face in such solutions. Now I will talk about the fundamental problem in this field in the light of these abstractions. So the problem is the consensus problem. So basically it is the problem of having a set of nodes or a set of processes agree on a value. It is a central component for many important tasks such as fault-tolerant leader election or state machine replication or achieving strong consistency or committing distributed transactions. For instance, if you are using tools like Zookeeper, it means you are already dealing with this problem under the hood. I will evaluate some consensus algorithms with a high-level perspective and talk about their safety and liveness properties. So safety means our processes should not make different decisions. They should all make the same decision, and that decision must be given or proposed by some of them. So it says that one node should not commit while some other node rollbacks. So they should all roll back or commit. And liveness means that the system or the nodes should eventually commit or roll back. So they should eventually make the decision. They should not try forever. But again, the bad news is we have a famous impossibility result here, which is called the FLP result. So FLP result says that if the system works in the asynchronous mode, you may not achieve distributed consensus within bounded time if at least one of your processes fail by crash stop. And it is because in the asynchronous mode, we cannot differentiate or we cannot distinguish between a crashed process and a slow process. And the algorithm may fall into a case like it sends a request, it sends a message to another process, and it needs the response of that message, but it cannot get the response because it can happen that the other process is just crashed. So it means that it will wait forever because the scenario is crash stop. So if some process crashes, it will never come back. So I just introduced a fundamental problem and said that it is impossible to solve. So is it a game over? Thankfully, no, because first FLP says that consensus is not totally impossible. It may not be possible under some failure scenarios, but it is with very low probability. And it also assumes the asynchronous system model, which is the simplest or the weakest system model where you cannot make any timing assumptions. But in real world, we are thankfully in a better position because most of the time we can make some timing assumptions and we can think of the partially synchronous model. So okay, how we can build consensus algorithms in the presence of this impossibility result? So there's a famous paper called Unreliable Failure Detectors. So they make some timing assumptions in the system and the problem becomes solvable. So they make a slight change in the abstraction and introduce this new notion, which is a local failure detector. So in this one, each process has some local failure detector, and that local failure detector relies on heartbeat messages and timeouts to make suspicions about other processes in the system, and those suspicions can be inaccurate. And the idea is these local failure detectors are there so that our systems can pretend to work in the synchronous mode, and as long as they give us sufficiently accurate information for a sufficiently long amount of time, our algorithms can make useful work. And as I said, they can make mistakes. So they can make two types of mistakes. First, a local failure detector can suspect from an actually running process. So this is about its accuracy property, and it may not suspect from an actually failed process, and this is about its completeness property. And based on the level of accuracy and level of completeness they have, there are different types of failure detectors, and in the paper they also calculate how many failures a particular type of failure detector can handle to solve the consensus problem. So this is the basic idea. So when we make some timing assumptions, most of the problems can become easier. So let's talk about some consensus algorithms. So I will start with the two-phase commit. So as its name implies, it consists of two phases. So in the first phase, a transaction manager or a coordinator asks votes of the participants. So if everyone votes for yes, it means everyone can commit the distributed transaction. So in the second phase, it sends the commit message. If any of them votes for no, it will send the rollback message. So this is a very simple algorithm. And it solves the problem and it satisfies the safety property. So it will never happen that some node will commit and some other node will roll back. But its liveness property is not that great. If the coordinator fails at some unfortunate moment in the system, this algorithm can block. So we call it a blocking algorithm. And we have another consensus algorithm, which is three-phase commit. So this one introduces a new phase. After the votes are collected, So in this new phase, it first publishes result of the voting before sending the actual commit or rollback message in the last phase. And it also relies on timeouts to make progress if there are any failures between any of these phases. And by that way, it solves the blocking problem of two-phase commits. So this is a non-blocking protocol, and its liveness property is okay. But the thing is, it can lose its safety property if there are failures in the system other than crash stop. So it cannot tolerate other types of failures we discussed. And last, we have majority-based consensus algorithms. So they rely on availability of majority nodes to guarantee safety and liveness in the system. For instance, to tolerate failure of a single node, they require 3 nodes. To tolerate failure of 2 nodes, they require 5 nodes. So if you lose 3 of your 5 members in the cluster, it means those algorithms will block. And if you recover at least one of them, they can work again. And the good thing is they are resilient to asynchrony of the system. They are resilient to crash stop failures, network partitions, crash recovery failures. So they are quite powerful algorithms. And under the hood, they rely on, or they make use of some variants of logical clocks. Like they call them like sequence numbers, terms, etc. And the most famous consensus algorithm is Paxos, which is again introduced by Leslie Lamport. And it has many variations, and Google uses this algorithm extensively in their products like Spanner, Megastore, Chubby, etc. And another consensus algorithm is ZAP, Zookeeper Atomic Broadcast, which is used in Zookeeper. So it's also popular. And we have a recent algorithm, Raft. Generally, consensus algorithms are known to be complex and hard to implement. So this Raft algorithm focuses on to build an algorithm that is easy to understand and easy to implement. And I think it achieves the goal quite successfully because we have a lot of open source implementations available on the internet and tools that rely on this algorithm. And last, we have the weave stamp replication. It is also an old algorithm, but it is not as popular as the other ones, as far as I know. But the good thing is, they share many similar ideas with the other algorithms. And this is not the complete list. There are, some other algorithms or variations of these ones, etc. In Hazelcast, we implement both two-phase commit and three-phase commit, but we do not have an implementation of any majority-based consensus algorithm yet. Maybe we do it in the future, but we do not have it at the moment. But the thing is, these algorithms are mostly used to implement or achieve strong consistency in distributed systems. But the thing is, they require a lot of coordination and communication among the nodes. So somehow they are expensive algorithms, and I think coordination should be avoided wherever possible to achieve horizontal scalability in distributed systems. So I have some more to discuss about this consistency topic. So this is how we arrive at the CAP principle. CAP principle was proposed by Eric Brewer in 2000, and 2 years later it was formally proved. So it talks about some fundamental properties of distributed data systems under some failure scenarios. So it talks about consistency and availability properties. So it says that a shared data system cannot achieve perfect consistency and perfect availability in the presence of network partitions. So network partition means that a cluster of nodes split into subclusters, and nodes in a subcluster cannot talk to nodes in the other subcluster. And if that failure scenario occurs, the distributed system should choose to be consistent, or it should choose to be available, but it cannot be both at the same time. For instance, consensus algorithms choose to be consistent, and they preserve the single copy semantics of the system. So the systems will still work as there is a single global consistent view of the data, but the drawback is in some parts of the cluster or in some parts of the network partition, you will not be able to access to the data if you talk to that part in your clients. And if the system chooses to be available, it means that you can access to your data in any parts of this network partition, but the single copy semantics of the system can be broken, so data entries can diverge from each other. Same data entry can have different versions in the system at the same time. So basically it becomes an AP versus CP problem. So systems should choose to be AP or choose to be CP. And it goes without saying that this idea or this principle has gained widespread acceptance in both academy and industry. And I think it's a very, very good principle to describe general behavior of our systems, under some failure scenarios. But still, it also receives a lot of criticism. And, there's always a discussion about the CAP principle. The thing is, CAP principle says that consistency and availability are just binary variables. So consistency means that the system is strongly consistent or it is not consistent. And availability says that the A of CAP principle says that the system is highly available or it is not available. So highly availability means that when you send a request to any non-failing node, you should get a response eventually. But the thing is, in the real world, instead of treating them as binary variables, we can consider them as a spectrum, and we can have different models in the spectrum. For instance, in CP systems, you can achieve strong consistency models, but the thing is, under network partitions, availability of the system can go down. But if you can relax your consistency requirements, you can achieve higher amount of availability if you are okay with variations of eventual consistency, which are client-centric consistency models. So they give a separate consistent view for each client, and they allow some anomalies in the system. And in an AP system, if you employ stickiness, you can achieve a consistency up to the causal consistency. So there are a lot of variations, and it totally it is totally up to your requirements and what the system can provide to you. So I can mention how Hazelcast handles with this CAP principle. So we are an AP product. So in case of network partitions, we choose to be available on both sides of the partitions. And under the hood, we implement the primary copy and async replication method. So I haven't talked about replication techniques in this talk, but I will briefly talk about this part. So primary copy means that in Hazelcast, each data entry is replicated to multiple nodes transparently, and one of these nodes becomes the primary, and the others become the backups. And the data is managed by the primary and replicated to the backups. So when there are no failure in the cluster, you will always talk to the same primary, and by that way you will achieve strong consistency. But this idea implies stickiness. So if a client cannot talk to the primary for a particular data entry, it means it will not be able to access to that data. And we also implement async replication. So in Hazelcast, each replica performs the updates with independent transactions. So the coordination among these replicas are minimum while updates are being done. So we achieve a high throughput in the system. But the drawback is, when you gain something in a distributed system, most of the time you give away from something else, and it generally becomes the consistency. So in our system, since because of this async replication technique, there can be replication lag in the system, which means that the primary and backups can have different states. Some backups can miss some updates sent by the primary because of some temporary failures. And even if we have some measurements or measures to resolve this kind of issues once we discover them, it is inherently present in the system. So it is always possible because of the chosen replication method. So there can be some data loss if there is this replication lag in the system and the primary fails. But I think it's a good trade. It's a fair trade because once you want to achieve something or once you want to improve some part of the product, most of the time you have to make some trade-offs. So in this talk, I've tried to give you a basic overview of, about these topics from a distributed systems builder's perspective. But if you deal with distributed systems, more or less, these are some of the topics you may need to be aware of. And nowadays, distributed systems are everywhere, so you don't have to build a distributed database to deal with these problems. We have distributed web applications, mobile applications, so we have multiple copies of our data in multiple places. So somehow these topics become also our own problem. And I can say that in this journey, learning the fundamentals is a good way to have a solid foundation about understanding the system and end up with a practical and a reliable product. So this is all for my talk. So I would like to thank the organizers of this conference to invite me here, and I also thank you to attending to my talk. So if you have questions, I'm more than happy to answer. So thank you again.